Welcome everyone. My name is Rolf Brink. I'm with ASPERITAS and I'm going to be explaining to you how we're dealing with optimization of service for immersion technology. In our case, immersed computing. Immersed computing is a concept developed by ASPERITAS, and it actually encompasses the entire portfolio of what we're working with. And before I can get into the server design part, I need to provide a bit of a context around the technology that we have developed and put on the market and that we're deploying today. I guess you all have seen our system downstairs. It's next to the main entrance to the big keynote area. The system we have is called an ASE24. It's an immersion system that is completely thermally insulated, that recovers nearly 100% of all the electrical consumption as heat and puts it into a water circuit. The system has been developed for a tier 3 to 4 level data center environment, was built for redundancy, resiliency, and high quality operation. It can facilitate 22 to 36 kilowatts inside each module. It's a modular system. You can stack them up to make a larger environment, which translates to approximately 31 to 50 kilowatts per square meter. And this system is quite unique in a way because it requires no mechanical circulation whatsoever. It's purely driven by natural convection flow. And a natural convection flow means that it's passive. There's no overhead energy consumed by a circulation pump. And it's actually incredibly efficient. The whole system is equipped with an intelligence system that provides a lot of intelligence information about what's happening inside that system, about the thermodynamics inside that system, and it connects to DSIM installations in any data center environment. And this system is fully optimized for high-density cloud and HPC purposes. And it requires optimized server designs, which is why I'm presenting to you about server design. We're completely hardware agnostic, and everything that we develop is focused on high temperature cooling and achieving very high return temperatures, which allows reusable heat. The system is a plug-and-play system, so it can be deployed very quickly and very rapidly. We're talking about approximately 1 hour deployment times. And it's fully integrated with power. All the power systems are fully integrated, means switchgear on a rack level. It includes PDUs, power delivery systems, which are fully managed and fully monitored per outlet, and it's fully EMC compliant. And this system connects directly into an existing facility water infrastructure, so no CDUs are required. And again, the integrated management features are all out of the box, and one of the main elements is that the liquid itself is included in the system. And the way that this works is actually quite interesting. So because we don't apply mechanical circulation, we rely on natural convection. And that natural convection is actually very effective. So what we do is we design servers in such a way, together with manufacturers and integrators, that we apply the heat sources as low as we can inside the liquid. And the liquid that gets in touch with that expands, rises to the surface, and then gets cooled down again by our convection drives, which are essentially water-cooled heat exchangers. And that's where the oil gets a higher density again and sinks towards the bottom, and that's how we generate that natural convection circulation. Now, the interesting thing about this is that it doesn't require any regulation because it's nature doing the job. We don't need to influence flow rates. We don't need to influence anything inside that dielectric liquid, simply because it's nature doing that. So the more energy you put in, the faster things happen. The less energy you put in, the less happens. And that's the foundation of everything that we're working towards. And that also explains why we're very much engaged in unique server developments. And this system requires no chillers, because most of our deployments, actually normally it doesn't require chillers. Most of our deployments, even the high energy ones, are still operating today with free cooling, also during the heat waves we had earlier this year. Now, I mentioned the intelligence system. When it comes to monitoring and managing the system, we have equipped the whole system with a lot of sensors. Thermal sensors, water detection, level detection of the liquid. We measure the incoming and outgoing temperatures, flow rates, pressure, and all that information is collected by the management controller. We also monitor the power input into the immersion system so that we can actually compare the input energy with the output energy, which we can calculate based on the water circuit management. And all that information is combined with a level of control. So even though we don't need to apply any regulation on that internal thermodynamics, we do apply control to the system for safety purposes. So there are relays that are controlling the power input to the immersion system, and there's electric valves to manipulate the flow rate of the water that goes into the convection drives. Because one of the features of this system is that we can optimize the water circuit. We can optimize for high return temperatures. So we maintain a constant delta of approximately 10 degrees C, but we can modify that accordingly, or we can let it be passive and just have a constant flow rate. The system also has a safety mechanism, also a fail-safe situation. When that management system fails for whatever reason, the system will always be up unless a customer requires something completely different. And we integrate another level of management into this management environment. One of the things that we do when we develop server systems and when we certify server systems is that we map every location of every temperature sensor on the board. Those temperatures can be collected with the IPMI interface. So we give an X and a Y coordinate to each sensor, and the system is aware of the location of every server inside that basin. So instead of just relying on our own temperature sensors that we've built into the system, we actually include all the temperature sensors from every server that's inside. And that allows us to create a 3D real-time thermal analysis of whatever is happening inside one of our systems. You can actually see this downstairs at the booth. That booth is monitored, is managed real-time, and these are real-time data. We can get more than 1,000 concurrent sensor readings from all the boards that are immersed. And this is something that this is the last thing I'm going to say about the actual system that we've put in the market, simply because we believe it's really important, especially these days. Everything that we do is circular, is towards sustainability. So also the manufacturing process, actually our manufacturing manager is even sitting here in the room at the moment. Every part, every piece that is required to build our systems, we think of how it can be reinserted in the supply chain when it reaches end of life. Either we refurbish or recycle or just reuse it in our supply chain. This is something that drives us. This is something that is fundamental to everything we do. Now, when we look at optimizing servers for immersion, the world starts really changing when you look at server design. Here's a couple of examples of air design servers versus liquid optimized servers. So on the top you see a couple of examples of OCP-based servers. I think these are both from Wiwen. And if you just look at it and imagine how air flows through that system, and then try and visualize a liquid having to move through that same system. One of the things that becomes really obvious is that liquid will have a very difficult time moving through that system. The way that everything is packed, the way that all the components are really stuffed into that chassis is suboptimal for liquid movement. It's good enough for air, not for liquid. So one of the features that you see with a lot of the immersion companies is that the basic chassis is built in a different way. It's an open structure that allows liquid to flow through it quite freely, quite easily. If you start building in constraints, you have to apply pressure to the liquid, and you have to increase the flow rates of liquid through certain compartments, and that applies pressure to components. That becomes a challenge. And these are just a few examples of some systems that we've been developing together with our partners, together with some manufacturers, and together with integrators. Now, this goes a little bit further than just designing a chassis. It's also about a lot of different factors that you are currently taking into account when designing a server for air. So for air, the chassis design is designed for stability and strength in a very closed structure. These systems are packed for because you need to handle them in a horizontal fashion, whereas an immersion chassis is oriented vertical, and that is much more designed for an open structure and reduced flow resistance for the higher viscosity medium that you're using. The forced airflow design versus a liquid flow design is something especially that we take to a whole different level, because we design it for natural flow. And that actually becomes very effective when you try to design something for any immersion system. If you design it for natural convection flow, you actually achieve the level of design where you can adopt any type of circulation mechanism. And one of these factors is that what happens if the cooling circulation stops working? What happens is that the thermal energy will keep rising to the surface and will keep removing itself from whatever component is generating that heat. Thermal shadow, two CPUs sitting behind each other, where the first CPU is actually preheating the air that goes into the second CPU. That can become a very big design challenge when designing a chassis for air. Within liquid, that effect is greatly reduced, because the actual thermal upgrade of that bit of liquid that goes through the first CPU is not so much. So the second CPU doesn't have a very big temperature difference compared to the first. So you can actually use that in the design of a mainboard or of a chassis. Thermal shock is one of these things that that's I think most of you are dealing with in air design systems, where you have high temperature fluctuations, where the materials are influenced by very high temperature differences and expand and shrink, and over time that may be one of the causes for a long-term defect. Within liquid, that is fundamentally different. So you can apply different types of standards to component level design. And the temperature sensors, obviously, in air are very much used to determine component health, whereas in, let's say, a memory module in air, if that becomes defective, you may be able to notice that because of the temperature increase of that specific memory module. Inside liquid, due to the high thermal capacity of a liquid, you may not see any temperature increase at all. But you can actually use that temperature to get an idea of what the environment temperature is of that same memory module. So looking at the type of chassis that we as ASPERITAS currently utilize, we call them cassettes because they're inserted vertical. And that's also where one of the most fundamental change comes to light. It's a vertical chassis. It's vertically implemented. One of the best practices when it comes to chassis design is that it should be fixated inside some kind of a rack, whether it's with guiding rails or whether it's a normal rack, but it should be fixated, because these things actually tend to walk around if you don't fix them in place. If the adjacent chassis positions are empty, these chassis can actually move around. And if they fall, they can actually also fall off their brackets if it's not designed to stay put. Because gravity comes from a different angle. Yeah, it's quite simple. Another best practice that we are promoting is the fact that all the interfaces should be dry. One of the things that you don't want to be dealing with on a daily basis as an engineer is that you need to be working inside a liquid. And another main topic is the extraction. One of the design features of any immersed computing chassis is that you can extract it easily from the liquid. And that should not always be a manual effort, because some of these chassis, especially with the earmark for very high density computing within OCP, these chassis are going to be very heavy. They're going to be difficult to deal with, especially if you need to extract them from a deep basin. The current dimensions that we use in our standard systems is a non-standard size. So we've actually determined the size of chassis based on optimal fluid dynamics and optimal thermal dynamics. And that means it's not 19-inch. We are also making a 19-inch and a 21-inch version, but when it comes to optimal thermodynamics, this is something that we've determined as a very efficient chassis size for the thermodynamic process for liquid cooling, or for immersion cooling, I should say. And it's all designed for optimal liquid flow. And this is a chassis, all our chassis designs are completely open source. We're still trying to find ways of publishing that, but hey, we're aligned to OCP now, so we'll see if we can feed that into the OCP organization, these type of designs. Whether it's this form factor, 19-inch or 21-inch, it doesn't really matter that much. But also when it comes to component placement. So another property of any open bath immersion system is the fact that gravity will always try and separate the thermal layers. So that means that the bottom of any immersion tank, whether it's a 3M Novec or an oil installation or any type of other open bath approach, the lowest oil will also be the coolest oil. The top layers will always be the warmest. And that's something that you can actually benefit from. If you design a chassis, you have to make sure to put the most temperature sensitive components all the way in the bottom. The advantage is, let's say you use mechanical circulation. If that circulation pump stops working, that hot component here in the bottom will have a very large cooling supply. And that will be able to run for quite a bit of time before that even gets anywhere near critical levels, assuming you're not running at the critical levels. So if their circulation system fails, you actually have a very big thermal buffer, because all that heat will go up to the top layers where the high temperature tolerant equipment is, and they can actually deal with that higher temperature. And there are instances, we've actually run tests in a high performance computing environment where we've been able to run the system for about an hour with no cooling at all. Now mind you, that was only about 10 to 12 kilowatts energy input, but still to have an hour window without any cooling circuit whatsoever, it's something that you should be utilizing. So the type of considerations for component placement are related to thermal tolerance, the thermal load. So how much thermal energy can something give off in combination with what is the maximum temperature tolerance. Like a CPU, usually fine to get to a temperature of 80-85 degrees, but you want to make sure that it never gets beyond that. But a power supply can very often, for short durations of time, operate in much higher temperature conditions. And it's all based on specific component designs, and one SSD drive may be tolerant to different temperatures than another. So these are considerations that you can apply to a very effective chassis design for immersion. And another element is component compatibility. Now, one of the main topics that we've come across a lot, especially in the OCP community, is optical cables. And this is also one of the things that ASPERITAS is doing a lot, seeking collaboration with manufacturing partners. Now, one of our partners is Leone. They're a cable company. They manufacture cables, and they've actually developed one of the first, I don't know if it's the first, but at least one of the first specifically designed optical cables for immersion. These are completely sealed. The first prototype was supposed to, they were supposed to show up yesterday morning with the first prototype. They were stuck in traffic. They literally received it yesterday, and it's now at our booth. And that's going to be available for the entire market for immersion technology. Optical cables that can be immersed regardless of the liquid that is applied, specifically developed in collaboration with ASPERITAS. Now, designing for liquids is something that we do on the chassis level with equipment, with components that are available to us today. Right. Right now, there's not so many manufacturers who actually design and develop mainboards or server systems very specifically for immersion. But what if there were? What if there were companies out there who started really developing for liquid? You can start coming up with some really exciting different views on how to deal with CPUs, with chip designs. One of those things is, how do you get access to the highest potential heat? What if you could run CPUs at a much higher temperature? If we look at how we measure, how we look at CPUs now, maximum temperature of an average CPU is somewhere around 80 to 85 degrees. Sometimes 78, sometimes 86, doesn't really matter. That temperature is actually the T-case temperature. That's the temperature that is actually on the top side of that chip. That's the maximum determined temperature for that specific chip. But that temperature measurement is actually taken on the exterior of the chip. So between that temperature measurement and the interior of the chip is still a layer of ceramic or another material. At least it will be electrical insulating. But that also means thermally insulating. So there is always a boundary layer on top of a chip that decreases, that is a thermal barrier. One of the ways to finding out what the actual internal chip temperature is just to put a thermal camera on the rear side of a running chip. And you can actually find that the electrical connections that get out of the chip on the rear side can get temperatures of about 120 to even 140 degrees Celsius. So very high temperatures. So one of the things that you can start, one of the questions that you can start asking, if you put this chip inside a liquid, let's start with air. That rear side of the chip is in contact with a little bit of air that sits underneath the mainboard, between the mainboard and the chassis. That air doesn't move. That air doesn't have any role in cooling whatsoever. But if you put this chip in liquid, it's in touch with the liquid that is still able to move a little bit away from that chip. So you could argue that this chip is actually already being cooled somewhat on the outside, on the rear side of that chip, on the mainboard side, on the PCB side. It actually means that some of that liquid is really getting closer to the real high temperature environment inside the chip. Considering the fact that we're all dealing with dielectric liquids inside immersion, could there be a potential to cool this chip in a fundamentally different way? What if we could penetrate the chip and reach the inside of the chip with a cooling liquid? What if we could open up that chip structure so you can actually get that liquid inside and start cooling it from the interior? Wouldn't that drastically decrease the operating temperature of the chips? Wouldn't that allow us to put a lot more performance into that same chip? And would it not allow us to get much higher temperatures inside the liquids, which makes it possible to reach very high return temperatures based on immersion cooling, based on liquid cooling in general? And these are the things that we're currently in the industry at a tipping point. Immersion technology is starting to break through. A lot of companies are getting more and more interested in liquids simply because chip designs are going towards 300, 400, 500 watts in the future. We all see it coming. We all know it's coming. Air cooling is going to be a limitation on using these high-powered chips. And that's the reason that most, if not all, the chip manufacturers are already dealing and already looking at how to utilize liquids to their benefits. This is only one example, but there's tons of examples. If you look at some of the deployments that we've done with record density GPUs, 288 GPUs in a half rack device without any active cooling, only because you start optimizing things for liquid. So the potential is immense. And this is the question I want to feed into this community to see, is there a way to utilize liquid to come up with some radical, better, new, higher potential designs? Now, to get back to today, what we've noticed and what we've experienced, what we've learned in the last couple of years, is that there's a lot of manufacturers, integrators out there who are really keen on getting more knowledge and more systems certified or compatible with liquid. But there's a big struggle going on within these companies, within the manufacturers and integrators, on how can we embrace liquid? How can we ever support liquid? Now that's something that we are actively doing as well, together with manufacturers like WeWin, like Gigabyte, like Supermicro, like many others. And that's a certification process. It's very simple. It's really not rocket science, but it's something that helps, that gives a guideline towards manufacturers to start supporting liquid. Basically, it's a process that is defined by 4 stages. First stage is simply a viability study. Can you put this stuff that we would like to put in liquid? Is it possible to do that? The board size, the component placement, materials used, paper exercise, thermodynamic analysis, some basic conceptual designs on how to do it, and we come up with a feasibility study. Second level certification is an actual prototyping process where we do a lot of material analysis. We investigate on a component level which materials are used to build up this CPU, to build up this capacitor, to build up these chips. And a lot of those components are obviously already known because we've dealt with a lot of them. But the manufacturers may not have. So we define a full report with material analysis, fluid dynamics, a practical test, a practical prototype build with a 24-hour high power, high temperature test where we provide a full report to the manufacturer. Third level is a 10-week duration test where the system is going to be used on a very high load in an environment where it's going to be taken out, disassembled, reassembled, maintained. We're going to swap out some components just to make sure that that system will survive that intense interaction for 10 weeks. Fourth level certification is a certification where this system has actually already qualified. I mean, we're pretty sure that this will work for a very long time and all the liquid effects have been mapped and there is none, at least none significant enough to prevent a deployment in reality. Non-significant enough, you're talking about stickers getting loose. I mean, you can cover that by documenting things. But level 4 is 24 systems, which equals one full deployment of one of our modules, completely equipped with this exact configuration, and that's been running operation at the customer location for at least 3 months without any issues whatsoever. When you achieve that level, you can be pretty certain that this is the type of configuration that can be deployed in the market without big concerns. Obviously, there's also such a thing as very long-term effects. That's something where simple knowledge comes in and expectations. But this is something that the entire industry must start picking up. And that's why it's also important also for an OCP community to start communicating about long-term effects that have been experienced, that have been documented. And that needs to be processed in a way so that other manufacturers, so that all the manufacturers and deployments and cooling companies and integrators can learn from that experience. So you know what to look for, you know what to avoid. And then that process should be something that is something that we're going to be feeding into the OCP community as well. So I'd like to conclude this small presentation with a call to anyone who is interested in immersion technology, but especially the ones who are knowledgeable about manufacturing service or who are potential future end users of immersion technology, to come and join the ACS workstream for immersion. Because this is where these type of optimizations are happening. This is where we're going to be defining these type of things, where we're going to be looking at making it possible for manufacturers and end users to start utilizing immersion technology on a much larger scale. Contact me or look onto the OCP website, sign up for the mailing list, sign up for the calls, and join these work streams, and let's get this thing going. That concludes my session for today. Thank you. Are there any questions? Yes?
I'm interested in the part load because it's based on natural convection.
Yes?
And when the load is low, then the delta T, of course, on the rack is small.
Yes.
So is there a possibility that at part load the natural convection collapse and hotspots risk appear?
No, it's impossible for the natural convection to collapse because it's a natural process, and we separate the downflow from the upflow by separating the convection drives in a different part of the same body of liquid. So in the area where the IT sits, where the compute sits, that's the only area where there's actually heating applied, and that's where the upward force takes place. So what doesn't matter how little it is, it will either stabilize or go up, but it will never. It will as soon as that the whole environment reaches a higher temperature than whatever is in the convection drives, that will leverage the cold environment from the convection drive down, and that will push up that heat eventually anyway.
So movement is always guaranteed.
Yes, it's nature. Okay. You can't stop nature. Well, you can put it out in space, but
now because you have to overcome the gravitational force towards the.
And that's what nature does. That's what nature does.
The force is always higher than the gravitational force to the bottom.
That's because we always apply cooling. So it doesn't matter how little heat goes in, as long as that water circuit is connected, the system will balance itself. Because it's not only a heat factor, it's also the cooling side that maintains that.
So you have always the heat sink outside, which is then basically is guaranteeing the delta T on the.
If your water infrastructure stops working, that's when you stop driving that natural convection. But then still the heat will go up, but you will never get to a hot spot where you can start overheating a CPU, because then you have so much heat accumulated along that component, then it will already be away from it. Yeah?
Yeah, thank you very much.
All right. If you want to know more, just make sure to come down and we'll demonstrate it live for you.
The slide about the reuse was very interesting. So I have some question. Water. At what temperature the water is produced for then the reuse, the hot water? And then about the oil. Is then regenerate, and you have already an idea about the life, and as the oil evaporates, what is the GWP of this fluid?
There's a lot of questions in one. So return temperature is not a fixed number. It heavily depends on the IT configuration you put in. Yeah, so let me start with saying that we have achieved temperatures of 65 to 70 degrees Celsius output temperature. Yeah, which especially with a European heat grids corresponds perfectly, because that's 50 to 70 degrees, and that's where we can really start feeding into heat grids, which means you don't need to get any cooling infrastructure at all. Evaporation rate of the oil doesn't reach the temperatures where it starts evaporating. So the evaporation rate is incredibly low, and besides that the systems are closed. So any vapor will not get out of the systems and will feed back into the body if you do exceed certain maximum temperatures. So to answer your question, I don't know that data from the top of my head, but if you would really like to know, make sure to send me an email and I'll be happy to have someone provide you with that specific information. But we use different types of oil for different applications though, so that figure may differ. So for the high density, really very high density applications, we use lower viscosity oil than for the low density applications. So we have a whole range of oils that we use, and we are also agnostic to oil, so we can also use third-party oils in our solution. Does that answer all the questions? Anyone else? Okay.
All right. Thanks, Rolf.
Great.